Mr. Blackburn? What? Yeah, I have it right. By the way, the green puffs. Yeah. The green puff? The green puff? The cream puff. Alright. Good afternoon, everybody. Guess what? It's hot here. We're all going to live. Sorry about it. I want the air conditioning to be on just as much as you guys. I can guarantee it. So we're going to be okay. Alright, now, excuse me, ladies and gentlemen, we're going to get going here. Okay? We're going to go through 2 examples from Solutions 2 because we did have kind of a long break here. We haven't been talking about chemistry for a while since you guys weren't here on Monday. We didn't have class yesterday, so we're going to go through an example of a dilution problem and an example of a molarity problem. Okay? Then we're going to go through a little bit of solution stoichiometry. You guys know how to do this already. Okay, we did solution stoichiometry when we did the fire suppression systems. So when we use the 1.25 molar HCl and the 12 molar HCl. So we're going to go through it a little bit more today again. Then we're going to talk about the lab that we have coming up on Friday. Your last quiz of the year, I'm telling you right now, is next week Friday. So don't come in on that day and be like, what, we got a quiz already? Well, I'm going to tell you every day this week, so I can just say, like, yeah, I told you so, like, next week when some of you still doesn't know. That's okay. Okay? So we got our last quiz next Friday. Okay, then the week and the following Monday after that, we're going to be working on a little project, and then it'll be the end of the year. Okay? Can't think of anything else right now. Okay, let's get started then. We're going to start out, like I said, with a molarity problem from Solutions 2. Okay, so when we are doing molarity problems, or we're trying to figure out concentrations of solutions or how many liters we need, we're always going to be using this M equals, big M is molarity, moles divided by liters. Right now, when we're looking at this problem, is how many liters will be required to create a 4.0 molar solution using 417 grams of barium chloride. Okay, so that means that we have a 4.0 molar solution. We want to know how many liters we need to make that solution. We have a certain number of grams. Okay? Before we can figure that out, the number of liters, we need to figure out how many moles of barium chloride we have in 417 grams. Okay, so we're going to have to set up a T-chart where we're starting at 417 grams of barium chloride. Okay, the answer that we get here is going to be in moles of BaCl2. That answer is what's going to get plugged in to our equation over here. Okay? So, the first thing that we need to do is find out the molar mass of barium chloride. So, if we look at the periodic table that's now deceased, actually it's on the ground over here, we found it out that it is about, it's 208.3 grams. And that's in 1 mole. Okay, so the 417 divided by 208, we're going to get roughly 2.0 moles of barium chloride. Now we have 4.0 equals 2 divided by the liters. Okay, that's not going to help us. We have to solve for our liters here. So if we use our handy little triangle over here, we see that if we take the moles divided by the molarity or the concentration, that's going to give us how many liters we have. So we're going to liters equals our number of moles, which is 2.0, divided by our 4.0 concentration. So in order to make this solution, we need a half a liter. Okay, questions on this one? Beautiful. Okay, dilutions. Okay, we use dilutions all the time in labs and chemistry. You're going to use them if you take AP next year. Myself, Mr. Gussie, Mr. Blacker, we use these all the time. Okay, so when we make your acid solution, so like last week we made that 1.25 molar HCl that we use in our fire suppression systems. We made that from a stock solution of 12 molar HCl. Okay, so we're diluting those. So we use this stuff all the time in chemistry. In order to do these problems, we need to use M1, B1 equals M2. Oh, there it goes. M2 V2. Okay, M1 V1 equals M2 V2. So that's our initial concentration times our volume equals our final concentration times our volume. So the problem says how many milliliters water would I need to add to 160 milliliters of 5.0 molar copper sulfate solution if I want to make a 0.30 molar solution. The first thing I need to figure out is how many milliliters, or what our volume will be of that final solution. Okay, keep in mind that when I do this, I'm already starting out with 160 milliliters. Okay, so whatever answer I get for V2 here is not how much water I need to add. Okay, so we're going to take our M1, it's 5.0, multiply that by our number of milliliters, it's 160. And that's going to equal our M2, 0.30, times our V2, which is what we're trying to solve. Okay. For these types of problems, if we want our answer in milliliters, we can leave this in milliliters. That's fine. We don't have to convert to liters like we will when we do use the molarity equation. Okay, then we have to convert. Okay, now solve for V2. We're going to take 5 times 160 and then divide it by 0.30. So that's going to give us the final volume that our liquid need to have this dilution work out. So I'm going to go V2 equals, and it's about, 2,666 milliliters. Okay, now that is not how much water I needed to add because I started at 160. So if I want to figure out how much water I need to add to my 160, I just have to take 2,666 divided by, or sorry, not divided by, but subtract the 160 from there. So that I started out. So I would need to add 2,506 milliliters of water to my solution to dilute it from that concentration of 5.0 molar to 0.30. Does anybody have questions on how I just did that? Super. Okay, moving on. Solution stoichiometry. You have this little flow chart on your worksheet here, okay? Now, we've been doing stoichiometry basically all semester, guys. So this shouldn't really be anything new for us right now. Okay, honestly, going from grams to moles to liters of a solution is even easier. Well, it's way easier than using the ideal gas law and doing liters of a gas, right? It's probably easier than going from grams to grams because we don't need to look at the periodic table at all and figure out, how many grams or what's the molar mass of our solution. Literally, well, this is liters of a solution down here, but literally our molarity equation gives us the conversion that we need to use in our T-chart. So when we are going from liters of a solution to moles, or from moles of a solution to liters, all we are using is this big M equals moles divided by liters. That gives us the conversion that we need. Okay, so we've done this before, like we said in fire suppression systems. We had to use 1.25 molar HCl. And all that meant is that in 1 liter of HCl, there's 1.25 moles. So there's nothing to really look up here. The problem is going to 9 out of 10 times give us big M. Okay, so if we're doing a T-chart and we see something is 6 molar, all that means is when we get to the point we need to go from moles to liters or liters to moles, we know that there's 6 moles in 1 liter. Okay, it's that simple for us. Okay, we're going to do 2 examples. One where we go from grams to liters of a solution, one where we go from liters of a solution to one of these other guys over here. Okay? So we're going to get to see going both ways. And it's easy to figure out when you need to, where you need to start. Okay? So let's just start out with number 1. This is going to be on your half sheet that you just got as you walked in today. Okay, so we're doing a couple problems off your homework for you. That means you guys only have like 5 to do. Okay, now. Okay, number 1 says, how many liters of 0.700 molar potassium chloride is needed to react with excess silver nitrate so that 8.76 grams of silver chloride are formed? Okay, I don't have the balance equation up here. So it's potassium chloride plus silver nitrate, and that's giving us silver chloride and potassium nitrate. Okay, now I'm going to write out the stuff that I'm given in the problem first underneath the correct compound. So I want to know how many liters of 0.700 molar potassium chloride I need. So I'm going to write 0.700 molar here, and I want to know how many liters of that I need. Okay, that means I'm going to be doing this step at the end of my T-chart. Okay, and I'm going to be starting out with this 8.76 grams of silver chloride. Okay, remember, this big M equals 0.700 moles in a liter. So it's giving us that conversion there. So we don't need to really be panicking with where are we going to find that at the end. It's given to us. Okay? Now, we're going to start out our T-chart with this 8.76 grams of silver chloride. Okay, first step, we need to get to moles of silver chloride so we can go from moles of silver chloride to moles of potassium chloride. So, we're going to need to divide by the molar mass of silver chloride. If we add it up and look on the periodic table, it's going to be 143.32 grams. And that's in 1 mole. Okay, the next step, mole ratios. So we're going to get from moles of silver chloride to moles of potassium chloride. So on the bottom we write 1 mole because it's just a 1-to-1 ratio. On top, 1 mole of KCl. Now, this is the only new thing that we're doing here is this next step. Okay, right now we need to get from moles of KCl to liters of KCl. How do we know what that conversion is? Because that's what the molarity or the concentration is telling us. Okay, so that concentration literally gives us how many moles we have. How do we know what goes where? Do we put liters on top or moles on top, or how do we know? Well, it's easy because the T-chart shows us right here. If moles is on top here, we got to get moles canceled out, so we have to write moles on bottom. So down here we're going to write moles KCl. On top, it's 1 liter KCl. How many moles are in that 1 liter? 0.700. That's a 7. It looks scrappy, but whatever. Alright. So, we're going to take it, plug it in our calculator then, 8.76 divided by 143.3 and divided by 0.7. And that would give us 0.0873 liters. Okay, it seems like a really small number, but if we think about that. We multiply that by 1,000, it's like 87.3 milliliters. Okay, so that's a comparable amount to like something that you would be using in our lab. Okay, so it's not really that small. Okay, questions on this one? Okay, so how do we know that we are starting or we're ending with this side of the flow chart? It's because we weren't given a number of liters, right, for our solution. If we're given liters of the solution, we're going to be starting with that. Okay, because we're going to be given that concentration as part of it, always. Okay. Now, the next one. It says mass of aluminum hydroxide required to completely react with 50 milliliters of chloric acid solution. Okay, so I need to write out the balance equation. It's AlOH3 plus balancing it. It's already balanced for you guys, correct? Okay. Thank you. Okay, so that's our balance equation. We got acid-base reaction happening here. Okay, so first thing we need to do is write out our information. We want to know mass of aluminum hydroxide. So I'm going to write grams and a question mark here. It's like we've always done. Then I want to write out the other information I'm given. I know that I have 50 milliliters of a 0.255 molar chloric acid. Okay, so I'm going to write that on here underneath 50.0 milliliters, and then it's a 0.255 big one. Okay, if I'm given a number of liters here and I'm given a concentration, that means that I can convert that to moles right away, and then I can get to grams of aluminum hydroxide at the end of our T-chart here. Okay, so we're going to start out with that 50 milliliters. Is that 50 milliliters okay like that though? No. We need to convert that to liters. So we're going to have to divide that by 1,000 here. So it's going to be 0.05 liters. 0.50 liters, and that's HClO3. Okay, what's the conversion of? The rest of the stuff we have here is 0.255, that big M. Okay, so what does that mean again? Well, remember that means that we have 0.255 moles dissolved in 1 liter of our solution. Okay, so here we're at liters of HClO3. We're going to write 1 liter HClO3 down here, and how many moles are in that 1 liter? 0.255. Comes right from the problem. Now we're at moles. Now it's just like we've always done, okay? We need to get from moles HClO3 to moles of aluminum hydroxide. So what's the mole ratio? It's 3 to 1, right? We have 3 moles of HClO3, so 3 moles HClO3 on top to 1 mole of aluminum hydroxide. Lastly here, we're going to write 1 mole on bottom. And then how many grams are in that 1 mole? So for this guy, the molar mass of aluminum hydroxide is about 78 grams. Okay, so we take 0.050 times 0.255 times that 78 and divide by 3 to get a number of grams for aluminum hydroxide. We're going to get 0.331 grams. Okay. Does anybody have questions on how I got that? So how we're using big M or molarity there, anything on setting up the T-chart, any of those types of things right now. Beautiful. If you have a device with you, we shared a link with you for the titration lab that's coming up on Friday. We're going to take some time and go over that in some detail right now, so we're all on the same page for that. Come Friday, we're going to go over procedure, a little bit of that, learn about what a titration is, and you guys will have some time to write that up in your lab notebook today if you want to, or work on solutions 2, or work on solutions 3, or any of those other things that we have. Okay? So if you want to take that out right now, you're going to go to the link that looks like this. Okay? So like I said, I would share with you, or you can just go to the website, and it's called the Titration Lab on the website. All right, so basically, what a titration is. We have a few things up here, okay? So I have them all up front anyways. You're going to be using something called a Buret on Friday, okay? Burets are highly calibrated. They let us find a very specific volume that we're going to be using, okay? So what we are trying to do is we're going to be using sodium hydroxide and hydrochloric acid. Okay, we are going to be using a known concentration of sodium hydroxide. So we're going to be using 0.1 molar sodium hydroxide. Okay, and we are going to be using an unknown concentration of hydrochloric acid. The whole goal for the lab is to do the titration and find the unknown concentration of our hydrochloric acid. Okay, so when you come into class, we're going to be using the formula M1 V1 equals M2 times V2. Okay, so you're going to come in class. You're going to titrate out a known volume. That's going to be your V2 for your acid. So you're going to titrate out 20 milliliters. You're going to put 20 milliliters of our acid in here. Okay, that's going to be what our V2 is. We're trying to find our M2. You're going to take and add a couple drops of phenolphthalein indicator to your acid. Okay, what this is going to do is it's going to turn pink in the presence of a base. Okay, the base that we're adding is sodium hydroxide. Remember, we know what the concentration of the sodium hydroxide is. That's what's going as our M1. That's our 0.10 molar. Okay, we're going to set the flask, the Erlenmeyer flask, underneath the Buret. We're going to take an initial reading, and we're going to start adding sodium hydroxide solution. As soon as the sodium hydroxide, and I have a video that's going to show this in pretty good detail for you guys. As soon as the sodium hydroxide hits the flask, the liquid in the flask is going to turn pink, and then it's going to go away. Okay, because it's going to turn pink right where that base is right away, but the acid's going to neutralize that base out, and the pink color is going to go away. Okay, you're going to continue to add sodium hydroxide until that pink color stays in the flask, and it's going to be relatively faint pink color. Once again, we'll talk about that with the video a little bit. You're going to take a final reading. Now that final reading is going to let you know how much volume of that 0.1 molar NaOH you have. So now you'll have an M1, you'll have a V1, and you'll know the V2 or how much volume of acid that you use. Using the M1 V1 equals M2 V2, you'll be able to find out the concentration of the acid. So that's the whole goal here. Okay, so we're basically neutralizing all the acid out. Okay, so we're going to watch a little video quick here. Pay attention, some of these questions are on the pre-lab, or some of the things that he's going to talk about are on your pre-lab.
An assistant professor of chemistry at Elon University. Today, we will be discussing the proper titration technique using the complete single Buret assembly kit available from Carolina Biological Supply Company. This is the first in a two-part video series on titration. The purpose of a titration is to quantitatively determine the concentration of an unknown solution, commonly called the titrant or analyte, by adding a volume of a chemical with a known concentration called the titrant.
And that'll be our sodium hydroxide.
To mark the endpoint of a titration, an indicator is added to the analyte. Let's review some of the equipment that's needed for a titration. Carolina's complete Buret assembly contains the basic equipment to get you started, including a Buret, ring stand, and a Buret clamp. A Buret is a long, narrow, graduated tube used to add titrant. It has a stopcock to regulate the flow of liquid. Notice that the markings on the Buret go from lowest at the top to highest at the bottom. The ring stand and Buret clamp are used to mount and secure your Buret. Other materials you will also need include a small funnel to help you fill the Buret, a 125 milliliter Erlenmeyer flask, which works best for titrations. The shape of the flask allows for more vigorous swirling than a beaker or other glassware and minimizes spill hazards. A volumetric pipette and pipette bulb to transfer a known volume of analyte to the flask. A wash bottle filled with deionized water, a beaker or flask of titrant and of analyte, indicator selected for your reaction, a reading card to help read the meniscus, and a sheet of white paper to help visualize the endpoint. To prepare your Buret for the titration, it is good laboratory practice to rinse your Buret thoroughly with deionized water, then with a small amount of titrant. After each rinse, open the stopcock to allow the liquid to drain out the bottom. If there is a lot of liquid clinging to the walls of the Buret, then thoroughly clean your Buret and repeat the rinse process. The accuracy of this technique is dependent on the titrant flowing into the flask and not sticking to the walls of the Buret. Mount the Buret in the clamp, making sure it is positioned vertically, and there is enough room to position your flask underneath the tip. Check to see that the stopcock is in the closed position. Insert the funnel into the top of the Buret and fill with titrant almost to the top. Filling exactly to the 0 mark is not necessary, but you do need sufficient titrant to complete the reaction. Check the column for air bubbles and gently tap to free them from the side walls. Remove the funnel. Place the Erlenmeyer flask under the tip and open the stopcock to allow a few milliliters of titrant to flow through, releasing any trapped air. Rinse the tip of the Buret with water. Empty the liquid into a waste container and thoroughly rinse the flask. It is not necessary to dry the flask.
Yeah, we don't do that.
Record your starting volume.
Okay.
It is important to accurately read the volume on the Buret. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This Buret indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the Buret. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the Buret requires 2 hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate.
So for us, like you can watch right now, I'm going to just talk over for that because what he's saying is a little bit different. We're just going to add a milliliter at a time. You'll see that the pink solution is staying in there right now a little bit. Okay, so you add a milliliter, you'll swirl it so that pink solution pink color goes away. Okay, and then you'll add a little bit more. That color pink that he has on there right now, that would be too much. Okay, that would mean that you went too far. So when it starts to get close, what you're actually going to be doing is you'll stop the titration and you'll start adding just a drop at a time to try and get it to turn just pink. Okay, so they're going to show a picture right now of like the difference here, the two look like. Just a second, so yeah. So like this, you look at the one on the right's where we went too far. So if you added too much base, it would be really dark pink like that. Why? Because there's a lot of base in there right now. Okay, when it's just neutralized, it should be a really light pink. It might even look clear to you right now, but in the lab setting, when you see this underneath a piece of white paper, you're going to see that it has a little bit of pink tint to it. That would be like you've done a pretty good job with your titration there. So you just added enough sodium hydroxide to neutralize it out. Okay, I mean, if you go too far, you can always add a little extra acid and add it onto your volume, but that's not you know that's not ideal, I guess. Here you can kind of see he's going to add basically a drop at a time. So this is good. If you watch, he's going to add one drop, and you see that the pink color stays a little bit. Now he's swirling it until it completely goes away. And what you would do is keep adding a drop at a time like that until that pink color, the pink tint completely stays. So that's when you know you've reached the end of the titration. Okay, that's where you take that final volume of the sodium hydroxide, and that's what we use for our M1 V1 equals M2 V2. Okay. We are going to do basically 3 separate titrations. Okay, so I know that they went over most of this on the video, but just to reiterate a couple of these things, you're going to come in, the first thing you're going to do is to rinse this guy out, okay? You'll rinse it with some water, okay, 3 times. That's to make sure that there's no water on the side or anything like that, okay? After you do that, you're going to rinse it with the base once. Okay, so you rinse it with the base. That's trying to make sure that anything that is left on the side is all just sodium hydroxide. So we don't want there to be any water left in here because that water is going to change the concentration of the sodium hydroxide solution. Okay, after you add the sodium hydroxide solution, you'll add it to up a little bit past the 0 mark. You'll tap it to make sure there's no air bubbles in there. Okay. Then what you'll do is you'll turn this guy, run this down to about the 0 mark if you want to start at 0. Okay, what that's doing is it's filling the tip a little bit with the sodium hydroxide. Okay, after you do that, you'd be ready to start your titration. So you'd go fill this with acid, you put your indicator solution in, you put it underneath, and then you'd start trying to find out where that neutralization point is. Okay, so like I said, we're going to be doing that on Friday. Okay, very, very last thing, and then you're going to have a little bit of time to work here. If we take a look at the lab sheet, anything that's purple on here is for reference. Anything where you see this red like this, now I know it's not red on yours because it's black and white. Well, I guess no, it is color because you didn't get a printed copy, so yeah, it's going to be color for you. So anything you see red here, that needs to be included in your lab notebook. So you need the pre-lab questions, a procedure, and this data table for Friday. Okay, does anybody have questions on that or anything else, the due dates, stuff that we have right now? Okay, we have the rest of the time then to work on solutions 2. This in your lab notebook, solutions 3, solutions 1 is due today. We've got a bunch of stuff that we could be potentially doing, okay?